Okay, so in this video we're going to talk about defining some of the commonly used C sub k values from that I mentioned at the end of the last video. And so the picture that I have drawn is essentially the x-axis, and you can see it's even labeled very similarly to what I had in the last video. Now we're going to have to go a little bit further now in a little more detail with our picture. But remember, for our sake, all of these widths are the same. So all of those guys are the same, and we call those delta x. So that's still delta x there, etc. Which means that labeling this point with respect to a, or in terms of a, is going to be a plus delta x to start. So if I start at a and I move over a distance of delta x, that's why we get the a plus delta x. This one would be a plus 2 delta x. The next one would be a plus 3 delta x, all the way down to a plus n delta x. All right. Now, I wanted to label the obvious ones like that before we got to these other ones. I want to focus on this x sub k and x sub k minus 1. Let's suppose that we had our rectangle drawn like this. And let's suppose now we're searching for a specific C sub k. We're going to define 3 of them in this case. We're going to define a left endpoint. We're going to define a right endpoint. And we're going to define a midpoint. I mentioned a couple sections ago that at the time, the left, the right, and the mid weren't going to be relevant because it was solely dependent upon the bigger number, the smaller number based on the estimate, and depending on the function, left, right, and mid didn't necessarily come into play like they are now. But now we're going to force it. Now we're going to start with a very specific position on the rectangle, left, right, or mid. So if I choose the left, let's say, the left endpoint would be right here. So we're saying that that is my height, right? My f of x sub k minus 1. Well, we also know that this guy is now a plus k minus 1 delta x. So for the left endpoint, we now have our sum from k equals 1 to n of f of x sub k minus 1 delta x, where the x sub k minus 1 is equivalent to a plus k minus 1 delta x. For the right endpoint, right, this would be your a plus k delta x, meaning our sum would be from k equals 1 to n, the f of x sub k delta x, where the x sub k is equal to a plus k delta x. So again, if I choose the left endpoint, that's going to be right here. That's like our curve coming and doing something like that, right? That's going to be the height of the rectangle. My x value is x sub k minus 1, and we're going to now use the a plus k minus 1 delta x, which is the same way, right? Just another way of writing it. We're going to be able to use that in our area computations. Similar on this one, but just on the right endpoint. For that midpoint, you can certainly work this out if you want to, but I have a feeling most people will be able to believe me when I say it. If I say that we are at the midpoint now, the m sub I, the midpoint, would be the a plus k minus 1 half delta x. Think about where that came from. That would be x sub k minus 1 half right here. And if I go up, it would be the a plus k minus 1 half delta x, just like each of these very systematically fit a pattern. So these are the 3 different ways that we're going to push these limits using these 3 different methods. And so I'm going to go ahead, clear the screen now. We'll get an example up there and really show you how all of this is tied together. Okay, so the example we're going to take a look at, and we're going to do this in a couple different parts. We've got the function f of x equals 5 minus x on the closed interval 0 to 5. We are going to approximate the area under this curve on this interval using 3 rectangles, right? It's an approximation if we have anything less than infinitely many rectangles, and using the right endpoint, okay? So a couple things that jump out at me right away. First of all, this 3 rectangles implies that n equals 3 in our particular problem. And for the right endpoint, we know that our x sub k is going to equal a plus k delta x. So I'm going to go ahead and get this set up nice and slow. I know that I've got my sum from k equals 1 to n, but n is 3 in this case. We've got our function now evaluated at a plus k delta x times delta x. Okay, now before I move further, let's talk about what a and delta x are. Well, the a value is here, so a is 0 in this case. B is 5. It's important to note that because we know also that delta x is going to be your b minus a was 0, over the n value of 3. So our delta x is going to be 5/3. Okay, so I'm going to go down to the next step, nice and slow. I've got f of 0 plus k times 5/3 times 5/3. So all I did was I plugged my 0 in there, I left my k, my delta x was 5/3, my delta x was 5/3. All right, so now this part here, this says go find function f, here it is, evaluate it at this right here. So every place I see an x, I'm going to plug in the k times 5/3. I'm going to keep my sigma notation. So I've got now 5 minus 5/3k. So that's, again, that right there, I've taken this guy and I've plugged it in. So I get 5 minus this thing right here, which is 5/3k, then times 5/3. Okay, so now the next thing I'm going to do is just a little bit of algebra. I'll take this 5/3 and I'll distribute it there and there. Keep that sigma notation there. So that's going to be a 25/3 minus 25/9k. And now we're ready to use some of our sigma notation algebra, the properties of sigma notation. So I'm going to take this sigma and I'm going to distribute it to this guy and to this guy. When I do this now, there's a few things that should hopefully start to fall apart. So a couple things jump out at me right off the bat. The 25/3 is a constant, so it can be pulled outside of the sigma notation. Same thing with the 25/9. It can be pulled outside. The k, however, because the index is k, has to stay put right here. So I'm going to go ahead and pull the 25/3 out. And so ultimately there's just that 1 sitting right there. You don't have to put anything if you don't want to, but a lot of times it's safe just to put the 1 to remind you. Then over here we've got a minus 25/9, the summation from k equals 1 to 3 of k. And now this is where you have to go back and you have to remember your summation formulas from a few videos ago. This guy right here is going to be your n times n plus 1 over 2 evaluated at n equals 3. So I'm going to go ahead now, I'm going to move up back to the other side of the screen. When it comes to the first term right here, notice there's no index there, but there still has to be 3 iterations of this series because we have 3 values. We have k equals 1, k equals 2, and k equals 3, ending at 3. So essentially what's going to happen is this thing right here is going to go to 1 plus 1 plus 1, right? Because a sigma means add. There's got to be 3 things. So 1 plus 1 plus 1. So 3 comes out of this. So we're going to have 3 times 25/3. So 3 times 25/3 minus this 25/9. And then from this guy, we've got our 3 times 4 over 2. 3 times 4 over 2. So we've got our 3 times 4 over 2. And now hopefully a lot of this will simplify out nicely. If I look carefully here, my 3 and my 3 go away, leaving me with just a 25 there on the left. On the right-hand side, the 2 and the 4 leave us with a 2. The 3 and the 9 leave us with a 3. So we've got our 25 times 2, which is 50 over 3. And 25 minus 50 over 3 is going to be 25 over 3, which is approximately 8.3. Okay, so this is our approximation using 3 rectangles and the right endpoint, along with, of course, our summation notation. All right, so again, that's an approximation. I'm going to go ahead now, clear the screen, and then we're going to do the exact area using infinitely many rectangles and using now the left endpoint. Okay, so now we're ready to take a look at finding the exact area under this curve on this interval. When we're trying to find the exact area, this is where our n has to approach infinity, so we're going to have that limit notation follow us all the way down. Additionally, I'm specifying us using the left endpoint. For that left endpoint, our x sub k minus 1 is going to equal a plus k minus 1 delta x. Now, I'm using the left endpoint. If we're approximating, so like we did in the last example, if we're approximating and we use the left endpoint versus right endpoint versus midpoint, you'll get 3 different answers. But if we're finding the exact area, if you use the left endpoint or the right endpoint or the midpoint, you'll get the same exact area, the same exact answer. It's the exact area overall. We're just using this technique of using the left endpoint, okay? So I want to be real clear on that. Approximations, you'll get different answers, left, right, or mid. Exact area, left, right, or mid, you'll get the same answer no matter what, okay? I'm just pushing the left endpoint in this one particular problem. Okay, so to get things started, we're going to have this limit out in front because it's exact, so we need to have the limit going to infinity of the sum from k equals 1 to n of our f of a plus k minus 1 delta x times delta x. Okay, now much like the last problem, our a value is still 0, but our delta x now, our delta x is going to have to be 5 minus 0 over n, right? We don't have a specific number, or we have n going to infinity, so we have 5 over n being our delta x. So carry this notation down, and we'll have f of 0 plus k minus 1 times 5 over n times 5 over n. All right, now much like the last time, I'm just going to now evaluate the function. Be clear on that notation there. So I'm going to evaluate f at this right here. So that's going to give us a 5 minus 5 over n times k minus 1 times 5 over n. All right, so this guy right here, this is our function having been evaluated at this right here. Okay? Now it looks like I'm going to have to take a few more steps algebraically to get this thing in a decent spot. First thing I'm going to do is distribute this 5 over n there and there. After that, I'll take this 5 over n and go into both of these, or I guess all 3 of these terms. So let's do that. Once again, carrying that notation down all the way. I've got a 5 minus 5k over n plus 5 over n times 5 over n. And now for the final distribution here, we have 25 over n minus 25k over n squared plus 25 over n squared. All right, so much like the last problem, I'm going to take this sum now and I'm going to distribute it there, there, and there. There's going to be a couple steps here now where we're really going to focus in hard on what can be taken outside of a series, what can be taken outside of a limit, how to get this thing into a really manageable state. So I'll keep this limit out in front, and I'm going to make some distribute quite a bit here, so I'll put some parentheses there. So I'm going to have the series from k equals 1 to n, 25 over n, minus the series from k equals 1 to n, 25k over n squared, plus the series from k equals 1 to n of 25 over n squared. Now, we also know that limits can be distributed as well, and so we could certainly do that now, or we can wait till the end. But what I want to point out is what can be taken outside of series. That's usually the part that's a little confusing to everybody. Out of this first one, we've got a 25 over n. The index is k, so none of this is affected directly by the series itself. So this is viewed as a constant with a series of index k. So that 25 over n can come outside. Here, the 25 over n squared can come outside, but the k has to stay. And then over here, much like the first term, everything can come to the outside of the series because it's dependent upon k. So I'll go ahead, I'm going to write that out now, keeping that limit off to the side. So 25 over n. Then we've got our sum from k equals 1 to n, and I'll go ahead and put that 1 there just as another reminder that it's going to be there. Then we've got a minus 25 over n squared, summation k equals 1 to n of k, and then plus 25 over n squared, summation k equals 1 to n, and I'll put that 1 there kind of as a placeholder. Okay, so then eventually now I'm going to end up moving up here. But for this first one right here, much like the last one, we knew there was a 3. So there had to be k equals 1 plus k equals 2 plus k equals 3. So ultimately, it was adding itself up 3 times. Here we have n. So we're going to add ourselves up n times. So we've got 1 plus 1 plus 1 times n. Therefore, you're going to have n come out of this right here. Okay, we're going to take, I'll write this on the side here briefly. I'm going to take 1 plus 1 plus 1 plus 1, and there's going to be n of them. So n times 1 would give us our n. So this piece right here, that's going to give us an n. Similarly, on this other side over here, this is the exact same series, so we know that's going to give us an n as well for the same reasons. And then here in the middle, this series, that's going to be one of our summation formulas, just like you saw in the last example. So I'm going to have my limit as n goes to positive infinity. From the first term, I have 25 over n times n minus 25 over n squared times n plus 1 over 2 plus 25 over n squared times n. All right, so this guy here, that 25 over n is this 25 over n. This n is that n. Minus 25 over n squared. There's our summation formula. Plus 25 over n squared, and then there's our times n. All right, so a little of this can be cleaned up. We'll have our limit here as n goes to positive infinity. In that first term, those go away, leaving us with just our 25. In the second term, we're going to have our, let me just write it as 25 over 2 times n squared plus n over n squared. Now, if you're thinking ahead a little bit with that limit, you probably saw why I wrote it like I did. And then for the last term, it's going to be plus 25 over n, where this n and one of these n's divide off. All right, so now notice we have n's in our problem still, and that's good because we have an n going to infinity. So now it's just a matter of computing the limit. The limit of a constant is the constant, so 25. And then minus the 25 over 2. This limit right here, as we go to infinity, you can certainly stop the video and go off to the side and rewrite it out if you need to, but we've probably done enough of these to know that this limit right here is going to go off to 1. So that's going to go off to 1. And then for the last term, if n goes to infinity, this whole part here goes off to 0. So for our final calculation, we have this 25 minus 25 over 2, which is 25 over 2. And so that's the exact area, which is also 12.5 if you really want to see it as decimal. That's the exact area under this curve on this interval. So a lot of what we've done in this section is very similar to what we did in the previous section. We're just now not so much forcing the visual graph every single time to compute this, where we've taken that general graph within rectangles and we've assigned formulas to them for a left, right, and midpoint. Now, this again allows us to hopefully avoid a lot of the messy pictures, and we can work in this summation notation. But it is very, very important to understand how these things work together. And if you did need the picture, you could certainly then create the picture as well.